and we'll have him on in just a moment. I just want to, first of all, just kind of keep an eye on people coming in right now and welcome all of you. So our discussion will be largely about composite materials and Ned's background and things of that nature. Before we begin, I wanted to mention to you one of the things I've started about a month ago is a new newsletter for Make. It's called the Make Things newsletter. It's at makethings.make.co. And check it out. You might already be getting it if you're a premium member of Make Community. But just a new way of talking and reaching out to our audience and talking about what people are doing. So let's bring Ned on if we can. We're up to 25 people. Wait just one moment here. Okay, welcome, Ned.
Hi, Dale.
How are you?
Dale. I'm doing great. How are you doing?
Yeah. Well, in the age of Zoom, you can have a background that's one thing, and maybe that's a good part to start with you. But actually, before I do it, again, for those of you joining, this is a conversation with Ned Patton, who is the author of this book. Hopefully it'll come up a little bit, The String and Glue of Our World, and it's understanding composite materials. And kind of as I wrote in the preview to this, I think materials are an area that makers could spend a lot more time learning about to figure out how to make different things, new things, just as there's new materials to do that with. So, Ned, I was teasing about your background, but why don't you explain that as a way of us telling us a bit about yourself?
Oh, I've been making stuff ever since I was a kid. My father was a physician, but his first degree, I guess, was engineering. He always had a workshop, and so I grew up in a workshop. I grew up with a table saw and radial arm saw and making stuff. I learned how to weld things together when I was 12 or 13 years old. So I've been doing this my entire life. And then with my dad, he wanted to make sure that I understood how things worked. And I was 15 years old, had my learner's permit, and I wanted a car. He said, okay, I'll buy you a car. We're going to pull it into the back of the workshop. You're going to take it apart. And when you have it apart far enough, I'll let you know. You put it back together again, then you can drive it. So I drove an Oldsmobile F85 with an aluminum block engine into the back end of the workshop and took it all apart. And here's a teenager. There was a little all thread in the block by the time I got done, but it ran when I was done. And I drove that thing for, I don't know, 3 or 4 years before I finally got rid of it and moved on to something else. And what I moved on to, of course, was British sports cars, and you have to learn that you have to carry a set of points and a condenser and a unison and a toolbox with you wherever you go, because the distributor is going to fall apart on you in the middle of nowhere. You got to be able to get it back together and make it run and make it home. So I did an awful lot of that growing up.
That's great.
My background here, I like to think of this as an Oregon forest because I grew up in Western Oregon. I grew up on the south side of Eugene, where there's a park that's basically a rainforest in Oregon and Willamette Valley, and so I like trees.
Okay, good. So just those of you that are arriving a little late, I want to welcome you to this conversation between myself and Ned Patton, and we'll be talking about his book, The String and Glue of Our World. But we do have the chat open. You're welcome to put in there where you're from or anything about yourself so other people can see. That's always useful. We have a Q&A feature in the bottom. We'll get to that eventually, and I'd love to hear your questions of Ned, especially relating to the subject matter here. Ned, why'd you write this book?
I've been dealing in composites now for 35 plus years. But my first introduction to composites was in 1981, 82. I was working at Battelle's Pacific Northwest Laboratory up in Richland, Washington. And I'd just gotten out of engineering school, had a master's degree in mechanical. And I was doing stress analysis of things, and I was doing a stress analysis of an Army anti-tank round, the one that gets fired from a tank gun. And because the accelerations, the forces, the loads, the stresses are incredible. So I'd done an analysis of that, learning ANSYS. For those of you that are as old as I am, that was 029 punch cards and the UNIVAC downtown, and I had stacks of cards that were 8, 10, 12 inches thick. And if you get one card, just off a little bit, the whole thing bombs out, and you got to go through all your cards and the printout of, that was a pain. Anyway, so I've been involved with computers and the stress analysis, and I went to the U.S. Army's Ballistic Research Lab, and I had been working with the gentleman that hired me there, and they wanted to. There's a sacrificial part, a boot, if you will, a shotgun wad of these anti-tank rounds that gets discarded, and that's extra weight. And so you want to reduce the weight of that as much as possible. And I was working developing an aluminum metal matrix composite part. And then he decided to hire me, and I went out to I went out to Aberdeen Proving Ground, where that is. And first day I showed up, he said, "I want you to go to Delaware and get your PhD." So I did. And University of Delaware, a lot of people call it the University of DuPont, but they have probably one of the finest composites manufacturing research institutions in the country. There's a few other universities that are really good. Northwestern has one, and there's a few others. But Delaware had this consortium, and so I ended up being the Army liaison to the Delaware, University Industry Research Consortium, and all that. Learned an awful lot about composites, and I have this abiding curiosity about how things work. I have to go, if I look at something and I can't figure out how it works, I got to go look at it again, try to tear it apart, try to figure out how it works, that sort of thing. That's sort of the way I've gone through life and through my career. I ended up working mostly in defense R&D, and mostly applying what I like to call interesting or advanced materials to difficult structural problems. That's sort of what I do. And right now I've landed at Northrop Grumman Marine Systems, and I keep talking about composites to everyone, and I was even talking about them to my wife, and she said, "You talk about those things so much. Why don't you write a book?" I thought to myself, that's not such a bad idea. So I took a piece of graph paper and I drew an ellipse on it, and the book just appeared. The chapters of the book just appeared on, with the little lines going out and little mnemonics about what I was going to write. And I sat down over Christmas break. I had a lot of it done. I figured out what I wanted to write, and I had a lot of it done in October, November time frame. we get about a 2-week break right around the holidays for doing plant maintenance and all that sort of stuff. And so I took all of that time and I just sat down and wrote the book, just wrote it.
Really?
But I did it because it just seemed like there's a lot of books that are how-to books and there's a lot of theory books, but there was no book that sort of tied all of that together, that started at the beginning and explained not only the what and how, but the why of composites. And so that's why I wrote it, is to I wrote it intending for it not to be a textbook and not to be put this part here and that part there and use this glue and this, and this is how you make a mold and all that kind of stuff. I start off with the Big Bang. Carbon was the third element, I think, created in the Big Bang. And it is the third or fourth most ubiquitous element in the universe. And carbon is really interesting stuff. So I learned, I had my first degree is biology, and so I'd taken organic in college, organic chemistry. And the organic chemistry came back, and I understood the chemistry of carbon pretty well. And so I did an awful lot of that. The first chapter is kind of the history, and then I go into the periodic table and why the elements are that make up why elements are so important.
Right. But maybe you could explain your metaphor that you use in the title of the book, the string and the glue.
String, well, that's people look at composites and they think, oh, this is a really advanced material, right? And in the old guys like me that have been in this business for a long time, we think of it as just strings all glued together. And if you use that as the way you think about composite materials, that's really all they are. We're taking strings, carbon fiber, glass fiber, silica fiber, Kevlar, whatever fiber, and we're sticking them all together with a bunch of glue. And I also use the metaphor of a tree in all of this, because if you take a look at a tree, wood is made out of cellulose and lignin. Cellulose is the string, the fiber, if you will, and lignin is the glue. And every tree's got a little different mix of each one of those. All plants have cellulose and lignin. That's how plant material is made. But that's nature. Mother Nature came up with this a long, long, long time ago. And all the analogs that we, all of the things that we make that we think are very advanced and all that, they're just analogs of what Mother Nature's already figured out. So I wanted to keep it simple for everyone so they'd understand all that.
Right. So you were saying you go through the periodic table. There's a lot of chemistry in what and what you do here.
Oh yeah, there's a lot of chemistry in it, but as long as you understand the elements themselves and what a valence is, and oxygen has 2 electrons it either gives up or wants to grab. Carbon is really interesting because it makes what are called covalent bonds, and there are 4 of there's electron shells. I'll get down into this a little bit. There's electron shells, and carbon has got carbon is 12. So it's got the inner shell, and then the outer shell is only populated with 4 of 8. Okay, 4 of the 8 total, and so it can either take an electron or it can give an electron out of that shell. But that interaction, that bond, is very, very strong. It's extremely strong when it bonds to something else. So that's why the chemistry of carbon is so important to composites. It's the chemistry of life, basically. So
So,
but I tried to explain it in a way that people would understand it and use, plain English.
yeah, I think you did a pretty good job of that, judging from what I've read. So I wanted to ask you before we get further in the book, you talk in the beginning and a little bit throughout of kind of organizing this book as a semantic tree. Keep on our tree theme here, but you said it was an Elon Musk idea that you had encountered.
Yeah,
Talk a bit
whether you
about
like
that.
the guy or not, he does say some rather profound things. He did say that to learn something, you have to look at it as a semantic tree. You got to get the trunk and the roots first and understand all of that, which is the basics. And then beyond that, what you have to do is put branches on it, put leaves on it, put fruit on it, all the other things that you need to add to it. And that's how you learn any sort of a field. And so that's how I tried to write the book. I started with the history just so that people would get an idea that composites have really been around for a long time. But I started at the trunk of the tree, which is the periodic table. And then I explain that and what the chemistry of each one of the important atoms are: silicon, carbon, oxygen, some nitrogen. That's then there's a few sprinkling of other stuff that's in there. But you build on that the basic understanding of how matter goes together and how chemistry works. And then you think of how to make something stiff, strong, what sticks to what. There's a whole lot of things you have to learn after that, but you have to understand, you have to start at the basics and understand the real, the fundamentals of atoms and how they bond together.
Right.
And what the strength of those bonds are and what the shape of the molecules is and that sort of stuff.
Right. So fiberglass is a composite material, right?
Yes.
Yeah. So that's been used for boats and lots of many things. And yeah.
Yes. Fiberglass is one of the earliest of the composites that was made. And it's glass fiber is just silicon dioxide fiber. It's all pulled out so that it's just a long string of glass. And then there's a polyester resin that sticks to it pretty well. You have to, there's a whole lot of things you have to do to make stuff stick to stuff, and that's, it's very important in the processing and all that sort of thing. But it's basically just glass strings stuck together with some polyester plastic glue. And the glues are typically thermosets, which means that they're liquid form until they set up. And it takes a certain amount of heat to set them up.
Mm-hmm.
Polyester typically room temperature.
And we jump to, say, carbon fiber, which is probably
sure.
something makers are, and that's a newer material, right?
Yeah, it's a newer material. Carbon fiber has been around for some time, but the carbon fiber that's made today is made from a compound called polyacrylonitrile. Basically, what the wonderful thing about organic chemistry is that nature loves this six-sided carbon ring, where there are six carbons all bonded together, and then there's hydrogen on the outside of it. Most people know of it as benzene, and if you put an OH on one of the carbons instead of a hydrogen, and replace that, put an oxygen and a hydrogen on it, that's phenol. And that is actually the basis of carbon fibers in most resins. Carbon fibers are basically sheets of these six-sided carbon rings either sort of all stuck together or all jumbled together or all wrapped up. Or actually a carbon nanotube is just a sheet of what's called graphene, which is just a plain sheet of these benzene rings, and it's just carbon and that's it. It's the carbon nanotubes are just sheets of those rolled up into little itty bitty tubes. And so the carbon fiber is just a stretched out long version of that.
Mm-hmm. We have a question from Richard Emmett asks, why use a composite rather than a solid material? Is it lighter, stronger, cheaper? Probably all those things.
Well, if you use just a one solid material like a metal or a plastic, you're stuck with the properties that you can get out of that one thing. Okay. If you're using a composite material, it's the different variations that you get are nearly infinite, depending upon what fibers you use, what plastic you use, how you put it together, all that sort of stuff. And the real use of composites is typically to make things lighter weight, stronger, stiffer, able to, like big old long booms that have to be very stiff, or an airplane skin where you're trying to minimize weight and yet it still has to be strong enough and stiff enough to be able to withstand the loads that are on an airplane wing. So, and wind turbine blades are probably the best example of that. You can't get a large enough wind turbine blade to make economic sense for wind energy without using composites. And the longer the blades get, the more you're driven towards carbon composites, carbon fiber, because it's lighter weight. And it's, the original ones were fiberglass with maybe a carbon spar cap. The new ones that are going offshore in Europe are all carbon fiber. Have to be, because these things are enormous. Turbine blades the length of a football field or more. So and the loads on those things are huge.
Yeah. We have a question come in about fiberglass. How does poor man's fiberglass fare? The fibers tend to be canvas or cotton, and the binder is paint. Example, skinning insulating board for making lightweight camping trailers.
Yeah, that's actually how they used to do airplane skins a long time ago. They would they'd take some cloth, some lightweight cotton cloth or whatever, and they'd stretch it over the top of something, and then they put a resin over it or paint or some sort of and that was an original composite airplane skin. I think that's the way the Wright brothers did theirs.
Oh.
So that's one of the originals, and it still works fine.
Yeah.
You can get away with whatever you can get away with. It's it would be better to use a linen fiber, because flax or linen is a lot stronger. As a matter of fact, there's actually been boats and canoes and a Porsche body that's been made out of linen fiber or flax fiber. So yeah.
Does turning away from fiberglass and just, how is the world of composite materials changing because we're more concerned about things like climate change and even the recyclability of materials or any of those issues that have to do with environment?
Yeah, I've been writing in my newsletter quite a bit about that lately, and that's going to be the subject of the next book, to be quite honest with you.
Really? Okay.
When I finally get it written, yeah. There is a move afoot. There are some issues that the composites industry is beginning to face. The carbon footprint of carbon fiber itself is enormous. For what you get, for the carbon that you get out of it, there's a whole lot of CO2 that's because you have to cook. When you make the stuff, you make an acrylonitrile fiber, you stretch it out, and you take all of these fibers and you get them all stretched out the way you want to have them. And then you have to cook this stuff in the absence of oxygen and cook off everything that's not carbon. Well, all those furnaces are all driven now with oil or gas. And acrylonitrile is a product of the petrochemical business and all that. So the carbon footprint is enormous for carbon fiber. There's a move afoot now to everyone now in the industry is talking sustainability. And they're talking about it, and some people are greenwashing it a little bit, but most of the majors are very interested in sustainability. And some of them are even moving over to plant-based resins and plant-based fibers, which is the future of the composites industry, especially carbon fiber and epoxy. There have been a few research results that have come out. There's one company that's actually scaling up a plant-based acrylonitrile for making carbon fiber that should have a zero carbon footprint at some point. And there are a couple of companies that are already selling completely plant-based epoxies. Now, the market's not quite as large as it needs to get to, but it's my opinion anyway, and from what I see in the industry, and from what I've heard and what I've read, and the people I've talked to in the industry, the industry is headed towards a plant-based future. So that's
interesting. You write in your newsletter about bioresin in their most recent issue.
Yeah.
And I might mention that nedpatton.com is Patton. Nedpatton.com is where you find information about his book and also the newsletter.
Yeah. I post the same newsletter on LinkedIn every week too. So.
Yeah. Okay. So you've been in the industry for 40 years working, and we were talking earlier how much travel you do. You can brag about that all your.
I don't want to brag about it. It eventually gets to the point where it's really not,
tedious.
It's all right. I just do it. Got to be done.
But give us an example of professionally what some of the kinds of jobs or work or products, things that you work on, things that you are consulting on. That you can talk about.
Yeah. I've given a couple of talks, gave two of them at the Carbon Fiber Conference in Salt Lake this last December. And I'm going to be talking at the SAMPE conference as well. And I sort of stirred the pot a little bit at the Carbon Fiber Conference, and I've gotten some contacts with some of the folks in the industry, and I'm probably going to be working with some of the suppliers. But as far as the industry is concerned, and jobs in the industry and that sort of thing, of course, aerospace is one of the big ones. But the sporting goods industry is, interestingly enough, very, very, very interested in composites. Tennis rackets, bike frames, you name it. The carbon fiber, most of it is fabric, but they're working through a whole lot of. They figured out how to make a full-on carbon fiber bike frame in one go, which I think is really amazing that they figured all that out. But there are entry-level positions in several industries. Aerospace is one, sporting goods industry is another. There are going to be a couple of other industries coming online once they figure that out. The infrastructure industry, interestingly enough, is also very interested in composites because they're very long life materials and lightweight. They've even gone to in some buildings, they're replacing steel girders with fiberglass. And there's fiberglass structural shapes that you can use to build buildings. And the problem with building buildings as tall as we're trying to build them is that after you get so tall, the self weight of the building itself starts really stressing the lower steel members, and they've got to reinforce those more. So making the upper floors lighter weight is going to help that industry quite a bit. And then, in California, we have earthquakes. So, making it so that they're strong and they're lighter weight, even allowing them to sway. That's another nice thing about composites, is that they stay elastic and they can move back and forth rather easily, especially the fiberglass.
Okay, great. Again, I want to welcome everybody that's in the Zoom room here, as well as people listening on YouTube in the live stream, particularly those in YouTube, excuse me, in Zoom here. You can use the Q&A function, which is the bottom of the Zoom app, to type in a question, and we'll raise it there. If you actually want to join us and ask your question in person, you can do that as well. We're also live streaming on Facebook in addition, so welcome to those of you on Facebook. But we'd love to have you ask some questions of Ned. Do you have any materials that you'd like to ask about? I wanted to sort of, at the end of your book, you sort of go into computing and how that's really changed. You mentioned earlier how you were using cards and punch cards, but the knowledge, the kind of structural engineering, if you will, around use of materials is really kind of increasingly embedded in CAD systems and other tools like that.
It is. It's increasingly being embedded in not only CAD tools, but the big analysis tools, ANSYS, Abacus, several others that finally have material models. When I was first doing this stuff, there were not good material models for layered composites. And that was one of the things I was doing at the Ballistic Research Lab was helping to, get us some decent material models, because we wanted to mess with thick composites. The thin things like small airplane wings or wing skins or those sort of things, you can use what's called laminated plate theory. And there were several different ways of doing that. They were pre and post processors and that sort of stuff. But once you get into something thick, then the process you use and the fiber directions and the matrix gets extraordinarily complex, and you can't really. You have to find some way to be able to do it, like layer by layer in a thick composite. You crash your computer. There's no way that you would have enough memory or disk space or time to let this analysis run to completion. So at the time, we were working on ways to shorten up that and get better material models. Since that time, of course, computers have gotten several orders of magnitude faster and a lot more memory space and all that sort of stuff. But the material models have matured as well. Started off, they were sort of university-ish, and I actually messed with one that was developed by emeritus professor at Stanford, Dick Christensen. I put that together in an 8-node brick element, and wrote my own finite element code just because I needed one, and it worked out pretty well. We did I put it up against ANSYS's, solid 182 or something like that, and turns out I got good numbers out of it. But that has changed substantially. The other thing that's also changed is the ability to go into your 3D CAD system, your modeling system, and assign material properties down at a small enough level that you can get reasonable results out of your analysis. And ANSYS has a good material model for that. Abacus has a really good one, and there are two or three others. But that's finally, come to the point where you can actually do a full 3D model of whatever you're building, whatever structure you have, and you can do an analysis of it, and you can get decent answers and know where you have problems or issues in your design. Because that's what the analysis of all this is refining designs to where your minimum weight and yet it all hangs together, and it handles the environment that it's in and the loads that it gets. So
yeah, I wonder if you might repeat the example that you have in the book of a rope swing as a way of kind of understanding that.
It's for those
for a kid, and then you might have an adult come along and sit on it.
I actually, my major prof at University of Delaware suggested that, and he's quite right, that people who aren't completely immersed in this stuff don't know what stress and strain are, or strength, or they really don't know what those really mean. And so I decided to make it as simple as possible for everyone what stress, strain, strength, all of that sort of stuff is. And so the metaphor that I used, I guess, is a rope swing, just a board with a hole in the middle of it, and you sit on the top of the board and you wrap the rope around a branch of a tree and tie it up there, and you swing back and forth, right? And so I explained, I used a 1-inch rope just to get them, make the numbers easy for people so that they can understand it. And I explained what stress is and strain is and displacement and strength, and the quantities that those of us that live in the solid mechanics business, sort of academic side of the whole thing do all the time. Let's say you sit on it and you're just a little kid, right? You only weigh maybe 50 pounds. You sit on it, and as soon as you sit on it, the rope stretches down a little bit. Well, the rope had an original length. You sat on it, you put a load on it, and stretched it out. Strain, that's displacement, is how much it's stretched out. The strain in it is a dimensionless quantity that we use all the time. Stress and strain we use all the time. The strain in it is the length divided by the displacement divided by the original length, and you get a number that's usually fairly small. And when we talk about metals, when we talk about composites, talk about fibers, we talk about strain to failure, 2% is pretty good, that sort of thing. But the stress that's in the rope is the load that's on it divided by the cross-sectional area. So it's pounds per square inch. That's how we think of stress, is pounds per square inch. And if you do a stress strain test, or you're trying to figure out, what your strength of your rope is, you pull on it until it breaks, right? And what you do is you take the stress at the point that it breaks is the area of the rope, or it's the force that you needed to break it, divided by the area of the rope, and that's some number. So it breaks at a 1-inch rope that breaks it at 500 pounds would be the stress was 500 pounds per square inch. Square inch of area of the rope, of the circle that the rope is. So that's sort of the basic concepts of stress and strain.
Okay, great. That's good to hear. I asked you before we got on about whether 3D printers create composite materials, and I just got a question from Richard Emmett again saying currently we have 3D printers for fluid materials. Do we need a new type of 3D printer for composites?
Actually, it depends on what you use as your precursor, and it depends on the 3D printer. There are some newer 3D printers that can print
multi-materials. Yeah.
Chopped fiber composites, and those are composites. And there are also 3D printers that can co-print. And I even heard of a 3D printer that you can print a thermoplastic on the outside of a carbon fiber toe or a fiber toe. It'll print it on the outside and lay it down where you want to have it. So you can build up a composite quickly. You know, there's a spool of fiber on this thing, and then there's that goes right through the print head, and then the material gets printed onto it, and you'll just lay it down. There's one that I know of that has been developed that they've demonstrated. I don't know that there's any on the market yet, but the composite material itself it's just two different components of material that you put together, and then once they're put together, their properties are different than the original constituents. So, and that's the beauty of composites. It's also composites' Achilles heel, if you think of it that way, because the beauty of it is there's an infinite number of different things that you can use to make a composite, but the Achilles heel is figuring out what you want to do and then making sure that your design is going to work. You know, that's where the experience and the forethought and design and all of that comes into composites, which is, you know, to me, it's fascinating. I love it.
That's kind of your chapter 5. You're making something out of composites.
Right.
You know, I'm just trying to, once you understand it, what are you going to do with it? And great. Robert Perry asked a question going back to the plant-based composites. What does the near future look like with regard to applications of composites in plant-based habitable structures, residential and commercial? So some kinds of housing and such.
I'm not really sure what's going on in habitable structures. Although you know, the nice thing about composites is that if you use the right sort of glues with the strings, you know, plant-based, you can make them so that they're watertight and weatherproof, and you have to add some things to, you know, little sprinkle of this and a little sprinkle of that to make them UV resistant and that sort of thing. But I don't know of anyone that's necessarily making like a plant-based composite shelter yet. That's an interesting idea. I think that somebody ought to start working on that. You know, flax fiber and a plant-based resol based epoxy would be great.
Right. No, not plant-based, but you used the example early on of concrete being a composite.
Well, concrete is a composite, yeah. And they are actually using quite a bit of chopped fiber now. That's one of the places where the recyclers have started to rather than using steel rebar, they'll use chopped composite, either glass or sometimes even carbon composite in concrete, and makes the concrete lighter weight and just as strong as steel reinforced. And you know, if you do it right, you can make it self-healing. And there's already people working on that, and there are additives to your cement and sand and rock that can take the place of steel reinforcement in some structures.
Mm-hmm.
So
where do you see kind of the most interesting ideas and applications coming from? Is it industry? Is it academia? Is it kind of entrepreneurial small companies? Where's
It's
things coming
mostly in the past, it's mostly been entrepreneurial small companies. And I think that that's going to continue because there are people, who come out of school like me and they get into industry and they learn a lot about it. And then they come up with a great idea. And,
but you can't do it
they,
where you work.
yeah. And if they think they can put it together, they start a company making this stuff. A lot of the composites fabricators started that way. I've got a good friend in Sacramento that started 3 companies. He originally was working in composites in the Midwest. So
sometimes just coming up with a different idea for what to put together.
Yeah,
and a different.
It's a different idea about how to solve some structural problem, or how to make something lighter weight that somebody might want to use.
Nick Cap asked an interesting question. He says, you talk about composites being stiff and strong, but what about composites that are like Jello? I'm thinking of tissue templates for cell culture.
Interesting. Yeah, that's well, it depends on what you use as a string and what you use as a glue. That's really it. It all depends on what you're using. If you could use some gel-like plastics or even something that's the consistency of agar, that sort of thing, and reinforce it with some microfibers or maybe microcarbon fibers or microfibers of something else, maybe cellulosic fibers or something like that. That would be an interesting thing to make a gel sheet, where you can, as a growth medium. If you use agar, then you've got the nutrients for trying to grow things and all that sort of stuff on it, and you could make these sheets. Be an interesting thing for potentially doing some organic gardening, or growing algae for food, or one of those sort of things. Might be interesting.
Yeah, this is kind of taking off a question on there. Are there sort of robotics applications that you're seeing in composites, or either in the assembly or things like that?
Yeah, there are not only robotics applications, there are applications for robots as well.
Right.
Yeah, more and more, the composites industry is going to automated fabrication, because it's always been the cost in composites has generally been the touch labor, having to lay up each one of the pieces of prepreg in a particular pattern and cut it right and get it laid in the right spot and all that sort of stuff. Tremendous amount of touch labor for the traditional way of doing an advanced composite. There are now automated tape laying machines and automated machines that do an awful lot of the assembly of the material itself. That is only going to increase as we get into more commodity products that are made out of composites. The automation in the manufacturing of those it's just gonna get more and more and more until most things are made out of composites and not metals. But as far as robots themselves are concerned, typically the limitations you have on robots are things like the stiffness of the end effector and knowing exact position of the end effector at all times, and making them longer and longer and longer so that they can reach farther, for the same amount of energy expended and the same sort of hydraulics, pneumatics, however you're driving them, all that sort of stuff. So making the structure of robots, automation equipment, is moving towards carbon fiber composites, and they can be. The nice thing about them is that they can be structured in such a way that you can even inflate them. Use. I've heard of ideas like this where you can use a pneumatic actuator to essentially twist an arm to get an end effector to be in the right position without having to have a knuckle or a joint, a rotating joint. That'd be an interesting application.
Well, that's interesting.
So, yeah.
Well, we're getting up towards the end here. I just want to encourage anyone who has questions. I have one here from Kevin, but please let's end with any questions here that you might have either in the chat or Q&A. Kevin asks, which industries or markets have been the most resistant to trying composites, and what doors could composites open for them?
Parts of the defense business, specifically the Navy, the parts of the infrastructure business, but that's changing. And
by infrastructure, you mean like pipes and
pipes, buildings, towers for electrical, all the things that we have to do for infrastructure. Especially things like pipelines.
Yeah,
those are pipelines are all steel because we know how to make pipelines out of steel, and so they're all steel. No matter what we run in them, they're all steel. I actually have a patent in a it's owned by the Gas Research Institute, but it's a patent in composite wrapped natural gas pipeline.
Wow.
So
it's a little bit off your usual thing, but as an engineer, as a person, what's your, and I don't mean this is funny in any way, but what's your reaction to seeing that bridge in Baltimore just collapse because the boat hit it?
What's my reaction to it? Is your reaction like we could have built that better? Well, we could have, but it was built a long time ago, back when the rules were very different.
Yeah.
And one thing that's, I think my reaction to that is probably it's mostly a political failure on the part of us and infrastructure.
Yeah.
We have a lot of aging infrastructure, and this particular bridge was a whole lot of things have changed since that bridge was built. Cargo ships are 10 times the size they used to be. And now bridges have to have some sort of a bumper system around the base of them to deflect things like big cargo ships. At the time when it was built, cargo ships weren't large enough to drop the bridge down, but boy, you put one that's got thousands of containers on it, and you get it out of control and it rams right directly into the bridge. It's, that's a failure in understanding how bad our infrastructure really, how much improvement we need, and how much we need to go back and rebuild the things that are already, we're using every day.
Well, that's a good point. I mean, it's kind of, you see reports on bridges, for example, that'll say they're, past their life, their life, but we keep using them until there's a dramatic failure.
Yeah, there's a lot of that needs to be, and it's going to be very expensive, but there needs to be political will and money put aside to do it.
Yeah. Well, Ned, I just want to thank you for talking to us about your book, about composite materials. I want to thank you for coming to Maker Faire last fall and giving a talk there. It's really interesting to mix up and connect to people that have such a deep background and formal training in something, and connect it with a informal community of makers that's curious and interested and wants to learn something. And I think your book is really good for people that want to understand this to a greater detail without being a
Thank you.
textbook and feeling like they have to, you know,
Yeah.
struggle
No
through it.
homework assignments.
Yeah, exactly. Just for the curious. But
Yes.
and I'd like to thank everyone who joined us today. Really appreciate you showing up. Sorry, a few of you had some trouble getting in. We'll see if you could send me email or anything about that process. I'll do it. But we've had upwards of 50 people on here, which is great. And please check out the book. Nick says he's got a copy of the book for his Kindle. That's a good one there to hear. And we appreciate it. So thank you, Ned. I appreciate you being here, and good luck to you on your travels. And maybe you get to stay at home a little bit now and then.
Yeah. I wanted to leave with one thought for everyone. Sure. Anybody who wants to have a conversation about composites, about materials, please feel free to contact me, and I'm more than happy to have a conversation. I'm one of those people where it takes a community. So let's build the community up.
Yeah, great. Well, thank you to folks on YouTube and Facebook as well, especially the people in our Zoom audience here. People are saying wonderful talk, and thank you, very interesting. Robert Jones, did I hear correctly? Yes, there's a maker fair this Saturday in Los Angeles, and I will be there. If you are there, let me know. It's at LA Historic Park, maybe. And it's organized by the LA Public Library. So pretty cool.
Oh, cool.
All right. Thank you all, and take care. Ned, good to see you.
Good to see you again.